this talk's going to consist of 3 rounds, and the first round is very much going to be the hard science, although it's not hard, and I wouldn't have told you that, so I shouldn't really ignore it. But then the second part, I hope, will show you really where there's kind of an absence in our abilities to use it actually on a large scale. And then we're kind of going to be forced in the third round to have to rethink how we might use what we learned from the small scale to inform kind of a more global picture of physics, and hopefully turn physics inside out. That's my main aim, because hopefully that will make more sense when we try and do it. So what we're going to start by doing is we're going to say what I mean by the classical universe. We're going to find out a little bit about what I mean about quantum, using an example of a coin and a photon being like a quantum coin. We're then going to see that how measurement produces like subjective classical world around us, and then we're going to kind of ask whether it's kind of different to view this classical world as a result of a quantum state. I think that it's massively important, more for us having listened to all of our talks today. I think it's a lot more important for physicists to know what we know about consciousness than it is actually to bring quantum mechanics to our experiences, because it seems we all have an innate ability to see some kind of something deeper than the classical universe around us. So hopefully I've learned a lot from today at least. So without further ado, I'm going to start the classical universe. We mentioned it. This is like normality as we understand it, the clockwork universe, and it's existed for hundreds of years. We assume that there's an objective universe around us, and we can describe everything as pool balls. Just to iterate that strongly, I'm going to, the example with a coin. I've got a coin, and we see that it's a head, and you know that its state is a heads. Sorry. And then we could also have a state where I don't tell you what's on the coin, but you assume that it has an objective function, but it's a probability distribution before you know what it is. But these are very well described classical states of the system. It's a probability distribution. Then we could also have like lots of coins flip, or we could have something where someone looks at one side of a coin and someone at the other. And all of this makes up our classical description of the universe. However, 100 years ago, we decided that none of those states ever exist as an actual description of what matter is in as a state, ever. They're only a good approximation at best. So then we invented quantum mechanics, and it does lots of things. But what it first does is it says a head. It also says we've got a mixed state where it's in a probability distribution. It contains all of this. So we've got all of our classical systems in this. But then when we introduce the important bit of quantum mechanics is where we can have a superposition. And we use the example of a quantum coin. This object behaves exactly like a coin. If I look at it 50% of the time, it would be heads, 50% tails. But I'm going to say it's both heads and tails at the same time. And we're all not going to believe me now, but it's very important that we kind of do. So it's not only is it both things at the same time, but it's built upon a structure, unlike a probability distribution, whereby like classic probabilities, 50-50, they're things between 0 and 1. They're very well described, and we add them up in this way. It's either impossible or certain or somewhere in between. However, these things have a structure whereby they can take on any value in the complex plane, which allows them to have negative amplitude. So what do I mean by a negative amplitude? It's like a probability, you know, but it's negative, and that doesn't make any sense classically. But importantly, it's not a probability theory. It does far more than that. So we're going to look at a couple of examples quickly. Well, in fact, one, it's Hom interference, and it's akin to flipping 2 coins at the same time. So classically, we know that 2 coins would give us some outcomes for coin 1 and coin 2, and then we would end up with what we expect, that we might have any one of these with a quarter probability. However, if you do the same experiment with a piece of light, you find that due to being able to create states that each one looks like a coin, but you can have these negative amplitudes, you kind of end up just getting these kind of outcomes where you formed a correlation from 2 independent systems that both, if we just looked at them and tried to analyze them with our classical worldview, then they would look like coins. So we've got these correlations, and we've created a state here that also contains the most important bit about quantum mechanics that I don't want to go into too thoroughly, but entanglement forms the basis of many of the great proofs of quantum mechanics. We mentioned Bell's theory, Greg mentioned EPR paradox. We saw a bit of Young's double slit, whereby you can take solid carbon atoms, which are the building blocks of life, 60 of them in a ball, and you can throw them through 2 holes, and they go through 2 holes, and that's like my body, right? Like, essentially, what can I throw, like, chuck a person through a pair of windows and they'll, like, interfere with themselves? Well, not really, but I wouldn't do that anyway. So we've got Young's double slit. We've even observed it 2 years ago in photosynthesis in plants. We can see it. It's happening. Things are in multiple states. And throughout all of these theories and all of these proofs, we see that we cannot explain them with our classical universe. And this is what, like, it's forced us to give up our whole notion of there being an objective reality. And this is why it's been a paradigm, and the 100 years following the kind of advent of these ideas have led to just a wealth of probing it to try and draw back to having an objective Newtonian universe. But we've failed to do so numerous times. And now we've got to get on to the important bit. Why don't we see this, or why don't we normally see it? And this comes down to the measurement problem. And we're going to look at what happens if this is me not knowing, and this is a quantum coin. So I'm going to measure it, and then the state becomes this. This is the framework. This bit of the state is me measuring a head, and it's a head. So this looks very much like a classical state from the point of view of this subset of the states. The state's bigger, but in a subset, it looks classical. So we've kind of created a classical state, the classical known state of heads. But there's a bit on the end there that looks very much like parallel worlds. And there's much controversy over the meaning of this kind of additional parts of a wave function that we can't interfere with. And we don't really observe them, and there's a lot of people believe it comes down to how big the system is, that the observation makes us kind of unable to interact with it. And that's the general worldview in the science, physics these days, is that kind of we can't interact with it. Either the wave function is collapsed and we just get rid of it altogether and we kind of ignore it and we just brush it under the carpet. But we kind of all know that that's not really sufficient, because you can't just ignore half the universe, right, every time you measure it. That would just be insane. And we mentioned, Greg mentioned the Copenhagen interpretation says the wave function collapses. Thermodynamics of the past couple of years, even like maybe 10 years at the most, is pointing towards it being a necessary in order to conserve like some really key properties of the universe. But importantly, in this structure, I can't interact with it, and therefore it's very restrictive. I'm nested in this little bit of classical space. And I'm only going to observe that bit where myself in one state and the coin in one state. So, like, classicality basically describes the world. Wow. So let's recap. Classicality is normality, as we know it. Quantum things do loads of things at the same time, and not in just probability theory. They interfere and they can form correlations that if, like, one part of a system and another part, the sum of a system contains more information than the whole. Let's continue. Let's get on to round 2, because we all want to be there, really, don't we? What's wrong with this? Because measurement leads to classical observations. The quantum world has no effect. But this is where we've got to question all of the premises of this argument. Like, I haven't said why I'm so big that I'll never interact with myself in 2 states. So what do large systems actually do? And I've only dealt with this idea of a coin, but we've got so much more than that. And my brain isn't like a measurement process that I can define. So this is actually built on a bit of a farce. But it gives you an idea of quantum. So what I'd like to do is do uncertainty principle again a little bit. Look at how uncertainty scales over distance, and then look at the measurement problem a bit harder. So what's not a coin? What's not a coin? We've got position, velocity, temperature. Classically, I can be exactly there with probability certainty. Okay. Quantum mechanically, it's impossible, no matter how much I measure it, to know where it is better than this. It's not even possible to know it where it is better than this, but it can never be in more well-defined a position than is defined by this kind of minimum bound on how much so. And this leads to a problem with measurement. Because now, uncertainty principle means that when I try and measure this state, there's going to be this little bit of like niggling doubt that I've tried to measure the table with this coin, but it's actually still tails. And this means that there's always this the state never becomes classical, no matter how much I try and measure it. And we're left with this blurriness around everything, where no matter how classical we try and make it by measuring it, we can never make it normal. It's always blurry, it's always in multiple states. And then suppose I try and measure something that is very far, if something has to keep measuring its, down a string, like Chinese whispers or something, we might have a big system and I measure it on one side. Then by the time the information gets to me, it's so blurred that at a distance, the kind of uncertainty isn't necessarily well defined. And we'll look at a bit more about how that happens on a global scale, because there are other it's not a line of Chinese whispers, it's actually a great network. But this, at the moment, this is assuming that my finger here can measure it very well. But that's just a massive generalization of what scientific apparatus is. Actually, we haven't asked what I am or what I'm measuring at the moment. And this is really where the problem is, that we call it measurement when our apparatus achieves some state of knowledge about a system. And we're always bounded by looking, even in our theoretical models, we've got this idea that we call it the Born-Markov approximation, and it means this is my quantum system and anything outside of it is classical. As soon as I receive information about it, it becomes classical, and it's just a massively crude generalization of what a laboratory does when it creates a quantum state. And it's this that kind of completely isolates us from being able to deal with big systems in any meaningful way. If I'm always trying to model it as the classical world is the key and it's a quantum object, then we're just it's impossible to get out of that shackle. And this is why I kind of like to go back to what we intend to do, which is I intend to learn from consciousness about what we can tell about the universe. And in order to do that, I think we have to turn back to what are the very purest principles that we can know that outside of my measuring apparatus, what is actually the nature of what's the actual measurement that I'm observing, at least? What is my experience observing? So with the measurement problem, I think we should point out, I'd like to point out a bit more the kind of difficulty with physics is that you have to construct it from these principles, whereas I like to get more philosophical and be able to deduce from our thought maybe what's going on. We don't want its framework of heavy measurement, so we're going to conject on what we do know. And my least favourite quote of the day is, "Whereof one cannot speak, thereof one must be silent," by Wittgenstein. And I think that he obviously wasn't a scientist, because he doesn't know about the scientific method and how you actually promote ideas and evolve a way of thinking outside of the kind of concepts that we already know about. So we've heard it before today, if you're in philosophy and ethics. I think therefore ... Descartes. So I think therefore that the world is classical. I'm going to say it. I do. This is how we observe it. It's, for most part, it's mechanical in my perception of it. And for that reason, what we know about the classical universe is that it's what you get in a quantum universe when something makes a measurement. And that little thing gets that classicality. So the up-generalization of that is to say that there's some set of measurements occurring, and over that set of measurements you can define a classical universe. So I'm going to say I'm performing some set of measurements on all of my neurons somewhere in between my mind and the outside world that makes up some boundary outlining me in, I don't know what space yet, but I'm doing some measurement process. And it's from this that we there we go. So my consciousness has got to be sat on some measurement process, because this makes the world classical. This is how I observe it. And I also measure everybody else, and we all measure the world around us and remember things about stuff. And we kind of form this very much a tight network of people that are kind of intertwined in this classical space. This normality as we absorb it. We observe it as this normal, global, consistent space that is all of our measurement boundaries kind of intertwined, as it were. But we also know that that boundary isn't a unique boundary to draw on a quantum space. There's a lot of them, and the boundary isn't defined as being outside of me or inside of me, but it's just some measurement occurring between some spaces that we can't yet define. And I'd like to look here at what we know about like our imagination and our thought process, and how this boundary can move inside our brain to kind of, I know that there's some classical perception of moment-to-moment thought going on inside my brain that must correspond to some ability to draw a classical boundary in some space. And it's a blurry boundary, but I'd like to get on then. So, we know then what's not the consciousness, what's not my day-to-day rigidity. It's the world that we don't see anything of. And I know nothing about this. I know nothing about what goes on in my subconscious, or about what we absorb from the world around us. I don't see any of that. It all goes in through my senses, but I'm completely oblivious to it. So I can't say anything rational about it. So I know that it's unaccessed. It's some sort of stuff that I've kind of subconsciously taken on. And it's kind of, it goes back in history, and it's still unaccessed. And it's lots of information and correlations that are otherwise kind of not necessarily the conscious part of my brain. And suppose then, now we're going to get weird. Because if that's the only bit that we know that's conscious, the only bit that's conscious, and therefore the only bit that's classical, then what if the rest of the information in the universe was all quantum information? What if it was? Like quantum states, we kind of mentioned they can be in multiple things at the same time, but they're like, multiple doesn't even begin to describe how mental quantum information in big systems is. It is mental. Let's look at how big some quantum system is. Okay. What we're going to do is we're going to get 250 of these quantum coins, and we're going to put them together in an arbitrary quantum state. And I don't think any of you could guess how big this state space is, or rather like how much information could be in it. Because it's astounding, and I'll tell you, it's equal to more than the number of particles in the universe. And I mean, in the observable universe, which is the universe that we normally say when we mean universe, it's in every star, it's the particles, it's the baryonic matter and the electrons, and that's 10 to the 100. This is what quantum space does. It adds a dimension every time you add a particle. It doesn't just add a couple of bits to it. It says, times this all by 2 again. Okay, times it by 2 again, times it by 2 again, times it in all the other dimensions that it kind of occupies. So it's actually 267 qubits, 10 to the 100 and some, 10 to the 100 and a bit. So it's massive. It's huge. And that information, in some ways, we use it in our quantum experiments to kind of do tests. We do things like we can use a couple of photons and send loads more bits of information than you would otherwise send with normal bits. So it's massive information, and it's kind of information that you can literally communicate in a lab with, this kind of stuff. It's huge, and what makes it kind of unique is like the entanglement properties of it mean that measurement of it doesn't have to be temporal either. And that's why you can, in some ways, you could imprint the answer to every question on a bit of information, give it to some quantum state, and then I could ask any question of it, and then that would collapse it. So in some ways it's interactive. You know, if this information is in a quantum state, then it's like, it's huge, and it's interactive, and it's historical. And I guess that gets on to why we might expect consciousness to do something good when it gets out of its like standard classical surroundings. So suppose we did like alter a function of our mind. Let's take a classic psychedelics. We see a decrease in brain activity. We kind of associate this with a lack of filter as such. And is that we're changing like the measurement process that our brain's making, and we may be retracting this kind of conscious boundary into ourselves and perhaps making it more blurry, as it were. There's that we haven't defined where it is yet, but it's just some boundary on a quantum space. So we see the kind of approach into the dreamlike states whereby we kind of don't have to associate our consciousness necessarily as much with a boundary to the outside world, but more to one to the inside world that contains far more than we might know. We can interact. And I think the last thing is that we often see in psychedelic experience a lack of being able to recount what has occurred to us. Like perhaps it's kind of in there, we've experienced it, but we don't have a kind of, I mean, we have a memory, but we don't have any way of like transferring this, like perhaps this multitude of simultaneous consciousnesses, this quantum type of consciousness, back onto a normal day-to-day consciousness, day-to-day classical world. So I'd like to go back to the orchard in which we all share the global consistent space with, and kind of suppose that we actually create something more kind of unique in an orchard, whereby we kind of whereby our consciousnesses don't have to be as regimented as they maybe had to. And I've got some funny artwork that I like for my friends. And I guess I really hope that we can learn more about quantum mechanics by looking out of the brain and not looking in from some apparatus at the world. And perhaps then we'll all be able to acknowledge that our brain is kind of, our consciousness even, is capable of observing far more than just a classical brain's worth of information. And it's very much an eye to very much more if we want to change the way that we think, and that if we change the way that we think, we are therefore confused if you think. I like that kind of thing. So perhaps let's not think in the classical way or something. Let's see what we learn. That's me.